Next, let's talk about the notion of first-class functions and some higher-level features of the Python language. Generally, a programming language is said to have first-class functions if it treats functions as first-class citizens. Python is a language that has first-class functions. So what are first-class citizens? Well, a first-class citizen, in the context of programming, is an entity which supports all operations generally available to other entities. And these other entities, in the context of Python, refers to objects. These operations that are available to other entities typically include being passed as an argument, returned from a function, being modified, and assigned to a variable. So again, in the context of Python, this means that whatever you can do with an object, you can probably do with functions as well. So let's take a look at an example. So here we have a function called well, let's look at the functions one at a time. So here's a function named myMax. So it takes in as input a and b, and it returns a if a is bigger than b, and it returns b otherwise. Here's another function, mySum. So it takes in as input a and b, and it returns the sum, a plus b, of the two inputs. So next we have the function reduce. It first prints out a certain message. We'll take a look at this message in just a moment. And then the remaining logic is something that we have seen before in a previous example. So the return value ret is initialized to be equal to none. And then we iterate through all the elements within the input list named lst. And a return is equal to just the element itself if the current value of ret is none. But otherwise, we apply this function binary operation, bin op, to ret and element, and then we return the final result. So first, let's just execute this function to see what the output is. Okay, so if the input list is 1, 2, and 3, and we use the function myMax, then the output is 3. And if the input is mySum, then we get the sum. And the same is true if we add more and more elements. So I think the functionality of this function reduce is quite clear. So it takes in as input a list, and for all pairs, we apply the operation defined by this input function. So first, what's noteworthy is that the first input to the function reduce is a list, which we are quite familiar with, but the second input to this function is a function. Here, mySum, that's the name of a function. myMax, that's also the name of a function. In Python, you're allowed to just pass in a function as an input, as an argument of a function. Now, something like this is common in some sense in other languages as well. So in the language C and C++, you can use function pointers. And in the language Java, you can emulate a similar behavior using interfaces. So the idea of passing in functions as input to functions is not an idea unique to Python, nor an idea exclusive to languages with first-class functions. But in Python, there's no need to distinguish the type of input. You can just pass in a function. So let's first look at the first part of this function reduce. So we'll comment out the remaining part. When we execute the function reduce, the first thing it does, it prints out this message. So this is an F string, and it prints out performing reduction with, and then it prints out the name of the function. The name of the function is retrieved by accessing the second input, bin op, which is presumed to be a function, and we retrieve the name of this function by accessing dunder name dunder attribute. So actually, functions also have attributes, and we are able to access the name of the function by accessing this attribute. Okay, so here the name mySum was retrieved by reading in this attribute. So we can actually probe the directory of the function myMax. This tells us which attributes this thing has. In this case, myMax is a function, and you might think that a function, the only functionality of a function is being called, but in Python, in addition to that, you can actually access attributes of this function, and in this case, we're accessing the dunder name dunder attribute from this function. Okay, now let's put this back in. So then what happens is, so the function bin op is being provided, and then except for the very first time this for loop is executed, then function bin op is used to combine the current value of ret with the next element from the list. So this example illustrates several features of first-class functions in action in the Python language. So first, a function is passed in as input to another function. The variable, in this case the input variable binOp, the variable binOp refers to a function rather than a regular object. And finally, functions have attributes and we can access them. Next, let's talk about closures. So first, I'll read you a definition of closures. A closure is a record storing a function together with an environment. The environment is a mapping associated with each free variable of the function. So the free variables are variables that are used locally but defined in an enclosing scope, with the value or reference to which the name was bound when the closure was created. Unlike a plain function, a closure allows the function to access those captured variables through the closure's copies of their values or references, even when the function is invoked outside of those variables' scope. So this type of definition is a kind of definition that only makes sense to those who already understand what a closure is. So let's try to understand what a closure is through the following examples, and hopefully once you understand what a closure is, then you can revisit this definition to further solidify your understanding of closures. By the way, these following two examples were inspired and copied from Corey Schaefer's YouTube channel. So this guy has some pretty good Python tutorial videos in his YouTube channel, so check out his content if you're interested. So first, let's execute this code and see the output. So the output is hello. Okay, so let's see why that is. So here we first define a function named outerFn. It takes in as input some input named message, and then it is stored as MSG. But for this example, for the moment, the input message, the variable MSG, will not be used at all. So the input to the function will be ignored entirely for the moment. Within the function, we'll be defining a inner function. So we define inner function. Inner function is a function that takes in no inputs and it prints out a certain message. And then we return inner function. And note that we are returning just the function itself rather than its evaluation. In this case, the function innerFn doesn't actually have a return value, so it doesn't really make much sense to evaluate the function and return its return value. Rather, we'll just return the function. So the inner function will be returned when we execute, and now when we execute this outer function, the effect of the outer function is that if we provide an input, the input is entirely ignored. A function is defined, and then the function is returned. So then fn, after this, refers to this inner function, and when we execute this function fn, we get hello. So, for example, if we print fn, then we get this function that was defined with an outer function, the function inner function that was defined with an outer function. We can probe the name of this function. So the function's name is inner function. So fn is a variable referring to this function named innerFn. So in this example, this variable MSG is not really used, but if we try to access the variable from here, well, the name MSG is not defined here because the name MSG the variable was created here within the function definition of outerFn, and then it goes out of scope. So it's not supposed to be accessible from the outside world, and indeed it is not accessible from the outside world. Okay, so this example does not contain any notion of closure. So now let's move on to an example that does have closure. So a closure is a function remembering a free variable. That's another way to understand what a closure is. And a free variable is, a free variable, which is also referred to as a non-local variable, of a function is a variable not passed in as input or nor created locally. Let's take a look at this example. Here I've slightly modified the definition of innerFn. So in outerFn, the function outerFn takes in as input some message. And then when the inner function innerFn is created, instead of printing a fixed message, we print the message MSG. And this MSG is the same thing as this MSG. And note, within the context of this innerFn, MSG is a free variable. It is a non-local variable. Because this function MSG was not passed in as input to innerFn, nor was it created locally. It's the function. This is a variable that resides in an outer scope. It resides. It comes from this outer. From over here. Once innerFn is defined, then the once inner fn is defined, then the function outer fn returns inner fn. Okay, so when we execute the function outer fn with goodbye, so here now the input string to the function fn matters. So this message is passed in here, it's assigned to MSG, and then it is used in the definition of inner fn. And then now fn is a reference variable referring to a function. So if we print the name of fn, we get this thing. We can also print the type of fn, and it's a function. And if we can evaluate fn, so when we evaluate fn, we print out the message goodbye, which was passed in here. But note that if we try to access the variable MSG from here, this doesn't work. The name MSG is not defined here. And that's, as before, MSG is out of scope here. It's not supposed to be accessible here. But the function inner fn, so normally the variable MSG should at this point be lost. It should be inaccessible. But the inner function fn, basically closes over the variable MSG. So the function inner fn basically remembers the variable MSG, and so the function inner fn is now a closure that remembers the variable MSG and is able to access this variable MSG even after the variable MSG has went out of scope. So the need to use closures do not arise that commonly, at least not so in my experience, but when closures are needed, they are incredibly useful. What I see is that many people utilize, when the need to utilize closures arise, they just use the feature without actually understanding that it is closures that they are using. Well, so I'm telling you about this feature explicitly so that you have an explicit understanding that this is a feature of the language Python, and when you use a closure, you actually explicitly understand that you're using a closure. So in the past, C++ and Java, being strongly typed languages, did not support the use of closures, but in more recent versions of C++ and Java, so I think in C++, the 2011 version of C++ and the version 8 of Java, which I think was officially adopted in year 2014, closures were added together with the addition of lambdas. So nowadays, C++ and Java, these other more traditional languages, do support closures, but it's a more recent addition. The next concept is decorators. So a decorator is a function that takes in another function as an argument, adds some kinds of functionality, and then returns the augmented function. Let's try to understand this through some examples. So first, in this example, we'll perform what decorators do without actually using decorators yet. So first, I'll execute this block, and the output is hello. So let's see how that works. So here in the first line of this code, we have fn refers to the function say hello. Okay, so say hello, that's a function. It returns a string hello. Now note that this string is written as double quote hello double quote, but this string, as is, doesn't have double quotes within the string, right? Because the double quotes are used to delimit the end of the string, but the string itself is just the characters hello. So if I were to just write fn is equal to say hello, and then execute the function fn, that will return the string containing hello without the double quotes, and the result of this print will be the message hello without any quotes. Okay. Next, we're going to apply the function add quotes to the function fn and then set that to be equal to fn. And once we do that, then the message is now surrounded. The returned string is now surrounded by double quotes. Now, how is this done? Well, the function add quotes is a function that takes in another function. So what it does is it takes in another function, and then within this outer function, we define an inner function. This inner function is named wrapper. It could be named whatever, but in this case, we named it wrapper. And then in the function wrapper itself does not take in any inputs, but rather it executes the function func, and then takes that return value and then prepends a double quote and appends a double quote. So here within, this is a string, the string is delimited by single quotes, and the content of the string is a single double quote character. The same is true here. So this is a string delimited by single quotes. The content of the string is just a single double quote. So, and then the function wrapper is defined, and then the function itself is returned. Note that we're not doing this. We're not evaluating the function and returning the result. That's not what we're doing. We're returning the function itself. So then add quote. So when the function add quotes is returned, we let fn refer to that result, and then we execute this function. So for further clarity, let's try this. Print fn dot name. We print out the name of the function fn. Let's remove this for the moment. So at this point, the function fn is made to refer, or the reference variable fn is made to refer to the function say hello. So of course, when we print out the name is going to be say hello. But if we do that here, well, fn no longer refers to say hello. What it does is fn is made to refer to the output of the function add quotes. So the function add quotes is being executed with the input being provided as fn being the function say hello. So when we do this, now the output, the output of add quotes is a function with the name wrapper, and the wrapper is the name of the inner function. And when we print out the result, now, this function wrapper is being executed. So the function wrapper is being executed. To do that, it then in turn executes the function func, which in this case is the function say hello. So when this is executed, when wrapper is executed, say hello gets executed, the hello is returned, and then that's prepended and appended by double quote characters, and that is returned as the output. Note that here, I guess perhaps this quote should go here. So note that here, the reason this works, despite the variable func being a free variable, is because closure is being used. So the input func is defined within the scope of add quotes, but within the scope of the function wrapper, func is neither an input to the function nor a variable that is locally defined, which makes it a free variable. So this variable func is made available by the closure feature. Okay, so here the idea of the function add quotes is that it takes in as input another function and it augments the function. The other function, say hello, is a function that returns some sort of string. In particular, it returns the string with say hello. But if we want to have a function but augmented in the sense that we want to add the additional functionality of appending and prepending double quotes to that function, then we can use this function add quotes and do this. And this adds that additional functionality to the original function say hello. So this is what a decorator does, but we did this without the explicit decorator Python syntax. Let's accomplish the same exact thing with the decorator syntax, the ampersand symbol. So the function add quotes and the function say hello is defined in the same way, but in this case, we'll use the decorator add quotes to decorate, to augment the function say hello. So if we don't have this, then when we have the function, when we have the function say hello, we execute it. Well, no augmentation happened, no decoration has happened, so the output is just going to be hello. But if we provide the decorator here, then the functionality of this decorator is that it will be augmenting this function say hello using this function add quotes. And now when we execute, we see the double quotes. Now more precisely, what's actually going on here, what the ampersand symbol syntactically does is if we do decorate A of the function B, then this is equivalent to first defining B and then passing in B as an input to the function A and then assigning that to B. So if we go back here, we can accomplish exactly the same thing by doing this. So say hello equals add quotes say hello. So this produces exactly the same output, and this is literally what the decorator syntax does. Okay, Okay, so let's see an example of decorator being used. So there are many reasons to use a decorator, and we'll see at least one in the context of PyTorch. But the use that I'll be illustrating in this cell block is the use of decorators as a debugging tool. So let's say there is some function, and we want to keep track of this function because this function is a very simple function in this example, but perhaps there is a really complicated function that is taking a lot of debugging effort to get right, and we want to keep track of the use of this function. So first, let's just execute this cell. So far, right at this point, I have not used any decorators, and so the print message is result of some math computation is something, and we use we call the function sum function. Okay, so the function is just being called, but perhaps we want to keep track of exactly when this function is being called. Maybe we want to monitor. Maybe this is a function that is potentially causing some issues, so we want to monitor exactly at what time this function is being called. Well, one possibility is to add things to the definition of the function, but that's something you often want to avoid doing because it's just additional code that you have to write, put in, like write and then remove, and you don't want to touch the definition of the function because you might mess up something else. So instead of adding things to the function definition, to the internals of the function, we can just use a decorator. So I'll decorate this sub function with the decorator timelog. So timelog is defined in this way. So timelog takes in as input a function as before, and then we define a wrapper function as an internal function. What the wrapper function does is it prints this message, and it says that let's just execute this first. So the result of having this wrapper is that we have this additional output. So the function sumfunc was executed at this time. Okay, so the name of the function was retrieved in this way. So this is an f string, remember. So we retrieve the name of the function by accessing the dunder name dunder attribute. And the exact time at which this line is being executed is retrieved by the date time and now function made available by the date time module. Okay, so and then after this, the function func will be executed, and that's our wrapper function. So when the wrapper function is called, we will eventually execute the original function func, but before we do so, we will leave this message. So this message is printed right before our main function, our function of interest is being called. So in this case, right before sumfunc is being called, this message will be printed out. So perhaps you do something like this and then keep track of when the function gets called and do some debugging. And when you're done with this, you just comment this out, and now the function is returned to its original form. And maybe you want to maybe this time log functionality, you write it once and then you utilize it for the debugging process of many other functions. So that way it's quite efficient. Another way you could use decorators for the purpose of debugging is you could instead you could choose to crash your program when a function gets executed. So maybe for some reason, when a certain function gets executed, you want to crash or halt the execution of the program because perhaps that function is something that should not be executed in the current form of the program, or maybe it's some important thing that you want to and you want to halt the program at that point. There are many reasons why you would want to halt the program for debugging purposes when a certain function gets executed. So let's first add in this decorator and see what happens. Okay, so the function so we get this message. So the function sumfunc was called. We will now crash the program, and then the function crashed. Okay, so how did that work? Well, the decorator takes in as input some function, and then it defines the wrapper function. But in this case, the purpose of this decorator is not to execute the function, but rather to print out the name that, okay, so this function was called, and we will now crash the program. And there are several ways to halt a Python program, but the most simple way is to just perform division by 0. So we perform division by 0, and this crashes the program, and then we return this wrapper function. So now that we have this decorator, the actual content of this function, sum function, will never be executed so long as we have this decorator attached. Rather, we will instead execute this wrapper function, which will print out the name of the function, and then move on to just crash the program without executing this function. So you use this and then do some debugging exercises, and then once you're done, you then remove the decorator, and now the function is returned to its normal state. The next topic is lambda expressions. So lambda expressions is a syntactic tool that allows us to compactly define simple functions. In other languages, and also in Python as well, lambdas are also referred to as anonymous functions. So here's an example. We define a function. So this is the code that defines a new function, and we make the reference variable f refer to this newly created function. So here, we define the function with lambda, and then after lambda, we specify the inputs to the function, and then we write colon. And after colon, we specify the function body and the return value. So the return value of this function is x plus y. So we define the function in this way, and then we execute it. Well, if this f of 1, 1, that's the output is 2. And the f of hello and then space world, that's hello world. Lambdas are called anonymous functions because the functions are not given a name. So if we print f dunder name, dunder, then it just says lambda. So usually a function is equipped with a name, but in this case, this function has no name. It's just said to be a lambda. Now, when you have a complicated function, a function which logic spans several lines, then you don't want to use lambda expressions. You just want to define a function in its usual way. But sometimes you have a function which logic is extremely simple, in which case defining a function using this like def and then function name input thing, this is a little bit wasteful and cumbersome. So when you have these really simple functions, then it's sometimes convenient. It's often convenient to define them just inline very quickly using lambda expressions. And the most common use of lambda expressions is its use in creating inputs to a function. So let's take a look at this example. So again, this is the reduce function that we had seen before. This is the exact same reduce function that we had used. But in this case, instead of defining the myMax and mySum function as separate functions, because those functions are very simple functions, so having that separate definition is somewhat wasteful. So instead, we can just define them in line. So let's take a look at this. So here we provide as input a lambda, a comma b, a plus b, and that's it. This is not that much longer than just typing in my sum, and it's overall using the lambda expression is much more concise than having a separate function definition. We can do the same thing to evaluate the maximum. So lambda a comma b, return a if a is bigger than b, and else return b. Okay. So to define functions anonymously, to define a lambda expression, we use the keyword lambda. And lambda is, of course, the spelling of this Greek word, lambda. So, and the origin of this word lambda expression, the etymology of the word lambda expression, comes from this thing called lambda calculus, which is a thing in mathematical logic. But in any case, so lambda corresponds to the Greek alphabet lambda, but the Greek alphabet lambda is used in machine learning and other areas of scientific computing as just the Greek letter lambda. So in Python, it is quite common to misspell lambda as lambda. So I can't really pronounce the difference accurately, but so this is the accurate spelling of the Greek alphabet lambda. And when you want to create a lambda expression, you must use the accurate spelling. And if you want to define a number that's written as with the Greek letter lambda, perhaps as a scaling parameter for regularizers in deep learning, then people will often use a misspelling and write lambda instead. Because lambda is a reserved keyword in Python, and it is unwise to use reserved keywords as variable names. So people will use this instead. I mean, this is still a little bit confusing, but it is what it is. People do this. I'm letting you know.